So welcome to this video on series RLC AC theory. Using a simple method, we're going to find reactances, impedance, voltages, the current and the phase angle. Now this is a simple method because it's easy and quick to do, and in another video I'm going to show you how to do the same using complex numbers in rectangular form and complex numbers in polar form. So we have a series RLC circuit with a resistor voltage, an inductor voltage and a capacitor voltage with a supply voltage called Vs. The phasor diagram on the right hand side. On the phasor we can show the voltages and the current and the phase angle. So that's the inductor voltage. In red is the capacitor voltage, because in this particular example the capacitive reactance is greater than the inductive reactance. We have the supply voltage in purple and the resistor voltage in black. So the phase angle is in between the resistor voltage in this case and the supply voltage. And if we subtract VC from VL, we get the opposite side of the right angle triangle, and we can see the series current. So just imagine this phasor diagram with all the lengths and the angles staying the same but spinning anti-clockwise several times per second. So this voltage triangle, we can replicate it, and it's exactly the same triangle as the impedance triangle. So we have the impedance as the hypotenuse, we have capacitive reactance and inductive reactance, and instead of the voltage of the resistor we have the resistance itself. So the same triangle exists whether you're using the voltages of the components or their reactances and resistances. So the resistor is the adjacent side of the right angle triangle, XL minus XC is the opposite side, and the hypotenuse is the impedance Z. So to find the impedance, the hypotenuse is a square root of the adjacent squared plus the opposite side squared, and the phase angle is tan to the minus 1 of opposite over adjacent. So the impedance is a square root of r squared plus the difference in the reactances squared, and the phase difference is tan to the minus 1 of the differences of the reactances divided by the resistance. Phase angle can be degrees or radians. The current is voltage divided by impedance, which is Ohm's law. Voltage across the resistor is the current times the resistance. The voltage across the inductor is the current times the inductive reactance, or you could call it the inductive impedance. And the voltage across the capacitor is the current times the capacitive reactance, or you could call it the capacitive impedance. So we'll do an example. So we're going to have the resistor value of 220 ohms. The inductor value is 318.3 millihenries times 10 to the minus 3. And the capacitor is 6.3662 microfarads, which is times 10 to the minus 6. Supply voltage of 100 volts peak at 50 hertz. And we're going to work out the reactances and then the impedance, the current. There's only one series current, and all of the voltages across the components and the phase angle. So to find the impedance we need to know the reactance of the inductor and capacitor at a certain frequency, 50 Hz. So XL is 2 pi FL, which is 2 pi times 50 Hz times 318.3 millihenries. And that is 100 ohms inductive reactance. It's 1 over 2 pi times the frequency times the capacitance, which is 1 over 2 pi times 50 Hz times 6.3662 microfarads. And that is 500 ohms capacitive reactance. now that we know those, we can find the impedance. Z is the square root of the resistance squared added to the difference of the reactances all squared. And that comes out as 456.508 ohms. So that's the impedance to the current flow in this circuit at 50 Hz. Now we know the impedance, we can also find out the phase angle, which is tan to the minus 1 of the opposite side divided by the adjacent side. That comes out as minus 61.19 degrees. So that's how much the series current is leading the supply voltage. And the current is V over Z, which is 100 volts divided by the impedance of 456.508 ohms. And that is 219 roughly milliamps. 219.05 milliamps is the current. There's only one current in this circuit because it's a series circuit. So we can find the resistor voltage is I times R, which is 219.05 milliamps times the resistance of 220 ohms. That's 48.19 volts across the resistor. And that's in phase with the series current, of course, from the phasor diagram. Voltage across the inductor is the current times the inductive reactance, 219 milliamps times 100 ohms. And that's 21.91 volts across the inductor, which is 90 degrees ahead of the series current. And the voltage across the capacitor is the current times the capacitive reactance, 219 milliamps times 500 ohms. That's 109.53 volts, and the capacitor voltage lags behind the series current. And we can find out all of these using Multisim. We can check that we've worked it out correctly and find the phase angle too by observation. So I've made this circuit, and what I've done, instead of having a 100 volt supply, I've multiplied that by the square root of 2 to give me 141.42 volt supply, because Multisim and Proteus and things like that give you RMS readings. So instead of having 100 volts, I've multiplied it by the square root of 2 so that all of the RMS values are actually peak values. It makes it easier. And we can see that VR is 48.19 volts, the inductor voltage is 21.9, and the capacitor voltage is 109.53 volts, and the series current is 219.05 milliamps. So we've worked it out correctly. But just remember to change your voltage back to 100 volts if you're going to look at the graphs. So click on Grapher, zoom all, and now we're going to find the phase angle. So I'm going to put between 50 milliseconds and 80 milliseconds to see one cycle. I've got x-axis cursors. The blue voltage is the resistor value and the green voltage is for the supply. So the resistor voltage is leading the supply voltage as we thought it would. And down the bottom we're trying to get both voltages where they cross the x-axis, where they're 0. And then we're looking at the time difference between them now is minus 3.3803 milliseconds, or minus 3.38 milliseconds. And we're going to use this to find out what that phase difference is. So the time difference we had, it was actually minus, but it's 3.38 milliseconds. And the time difference compared to a whole period is the same as the phase angle compared to a whole circle of spin. So the phase angle is 360 times the time difference between the waves divided by the period. And the period is 1 divided by the frequency, which is 1 over 50. So the period is 0.02 seconds or 20 milliseconds. So if we put the time difference and the period both in milliseconds, it'll give us the phase angle. 360 times 3.38 milliseconds divided by 20 milliseconds. It should be minus 3.38, but I put it as 3.38, but it doesn't matter because we know it's negative. It gives us 61 degrees roughly, and from observation that's very close to the theoretical value. We had minus 61.19 degrees. Just to show that that was actually a negative time difference, gives us minus 61 degrees. But we can make it better by going into the simulation settings and changing the time step to a smaller amount of time, so it does more calculations per second, so we can more accurately find where the voltages cross the x-axis. It takes longer to simulate, but it has more resolution or granularity. So I'll do that and then I'll simulate again up to about 100 milliseconds. I've sped this up, but it does take a fair bit longer. Then click pause, go to the grapher, zoom all, and select a part of time that we want to look at, say from 50 milliseconds. I'm going to put 75 milliseconds here, just to give part of a cycle. And we want to find where the resistor voltage and the supply voltage cross zero. But it's easier to do now that more calculations have been made by the simulator. So we're looking at the difference in time is actually minus 3.39. So we've made it slightly more accurate to find the phase angle. So if I do minus 3.39 milliseconds times 360 degrees divided by the period of 20 milliseconds, it gives us minus 61.03 degrees, which is pretty close to what we'd worked out. So we've worked out all of the reactances, the impedance, the current, the voltages and the phase angle, and we've proved it with Multisim. So thanks for watching, and I hope this was useful.